Hi everyone, this is Munawar Hafiz. I'm recording this talk ahead of time from Bay Area, California, where the headquarters of OpenRefactory is located. In today's talk, I'll be presenting our recent work on finding and fixing bugs in the top 2000 open source projects and how it is cleaning up the software supply chain dependencies that exist in almost every one of your proprietary software. But before I go ahead, let me give a little bit of background about myself. I've been working on automatic bug detection and fixing for close to 20 years now, all the way back to my PhD from University of Illinois at Urbana-Champaign. My PhD thesis was the first that asked the question, why stop at bug detection? Why can't you also automatically fix bugs that are in the code? That led to the foundation of OpenRefactory, on which I worked on when I was an assistant professor at Auburn University. In 2012, my student and I built the first general purpose tool that fixed multiple categories of open source security problems in C code. Specifically, I was focusing on integer signedness mismatch, witness mismatch, overflow, and underflow issues in C code. That particular research work won the best computer science research in all disciplines of computer science, and it was awarded at the Turing Award ceremony in 2013. Here you can see my student and I taking a photo with Vincerf, the father of the internet. Later I joined Coverity, which is the #1 bug detection company specifically for C and C++ applications. I started OpenRefactory after getting an award from the National Science Foundation. Our solution is a SaaS tool that detects bugs in your software, and for about 50% of the cases also synthesizes a fix automatically. The tool is called Intelligent Code Repair, or ICR. It is now available for detecting and fixing bugs for Java, Python, and Go code. I'll be coming back to this tool in the talk and how this tool helped us do supply chain security at scale for open source projects. So let's go to the biggest threat of our time, which is coming from the open source project. There is a very well-known XKCD comics that is shown here that people use to demonstrate the dependency of open source projects. All modern digital infrastructure is based on hundreds, if not thousands, of open source projects that are underneath. A current research from Harvard Business Studies showed that the collective value of open source software is about $8.8 trillion, and that's trillion with a T. Of all the tools that we create or applications that we write in proprietary scope, underneath that is open source. Research data shows that open source software contributes to about 70 to 90% of software, depending on what kind of applications you're building. However, unlike software applications that are written by organizations, open source software is maintained by a single maintainers, sometimes a group of maintainers who are doing this thing as an aside from their day job. Because of that, it is sometimes easier to attack an open source software, infiltrate into that, and then through that attack some proprietary software that is dependent on that open source software. If you look at popular open source software, 95% of the open source application dependencies in the world is actually maintained by only 5% of the maintainers. Therefore, you see that there's a small set of very critical software that are out there. And any breach in that would then allow a backdoor to millions of other software that are dependent on that. This is an extremely serious problem, as was identified collectively by the industry in 2021 in December. On a quiet day in December 2021, the world collectively woke up and started asking the question, am I using Log4j in my application or not? What happened was that the log4 shell vulnerability, which was identified in log4j, which is used by hundreds of thousands of software that are out there. And all of these application developers were suddenly tasked with updating that application and getting to a new version that does not have that vulnerability. However, a solution was not readily available, and it took the industry about 2 weeks to figure out an appropriate fix for that. In between, the industry made 4 mistakes, as in they prepared a patch, but that was found later to be insufficient. The log4 shell incident itself was probably $1 billion bug. However, the average cost of a security failure is still not insignificant. It's close to $10 million now. Yet, every week in the National Vulnerability Database maintained by the NIST of United States reports about 150 security vulnerabilities. What log4 shell did was that it made the industry aware of the supply chain dependencies that has to be made secure now. So we have these artifacts that are above this line that we are building, but underneath there are many other open source software on which we are depending. Software composition analysis, or SCA tools, look at these supply chain dependencies, match if there is a vulnerability that is known in any one of these dependencies, and then report to you so that you update that dependency. That's pretty simple. The problem of the SCA tools is that they only rely on known vulnerability data. But before there are vulnerabilities, there were bugs. There were probably some bugs that were reported to an open source maintainer. The open source maintainer fixes a bug and then issues a CVE, or a common vulnerability enumeration, to notify everyone of that potential problem that has been fixed in the software. It's only at that point the SCA tools notice that particular CVE and then make that available in their report. But there is a big air gap that lies between when the bug is found to when the SCA tools pick up the signal of a vulnerability. If we found that information when a bug is found, that would have been much better for us because it gives us more reaction time. So how about we proactively look for bugs in a large number of open source projects using static analysis, or SAST tools, report the bugs that have been identified to the maintainers, work with the maintainers to get those bugs fixed, and then some of those bugs, when they become vulnerabilities, are later picked up by software composition analysis tools. If that proactive scanning report is available to you, that allows you to shift left and gives you more time to react to the bugs or vulnerabilities. This is going to be very useful because you don't have to work under duress when a CVE is found in order to mitigate that. You can get ahead of time information and take measures appropriately so that you don't get a bad surprise. We are calling this project Cleaning the Beach. OpenRefactory is looking at the open source software landscape, which is untidy and messy, and then scanning and identifying whether there are problems lurking in the software in the first place. If no problem is found, it cordons a section of the beach that has been found to have no problems. That information itself is valuable for end users who are consuming this information and then using that information to pick and choose an open source dependency that they want to use in their proprietary code. This work has been supported by the Alpha Omega project under the Linux Foundation. So here's a summary of what we're doing. We are analyzing the top 2000 Java, Python, and Go projects with OpenRefactory's Intelligent Code Repair, or ICR, as well as other static analysis tools that are available in the Omega toolchain. We are reporting many different kinds of bugs and then working with the maintainers to fix the bugs. But the criticality of the problem is that we are able to do that bug fixing at scale to thousands of open source applications. So let's look at this bug fixing at scale aspect. There are two ways where we can look at a bug and then fix that in open source software. One would be a depth-first approach, where we detect and fix a single vulnerability or a single bug in all projects that harbor that particular problem. Another one approach is to detect and fix many different bugs in many different projects. Our work focuses on approach 2, which is the more comprehensive approach. As far as the depth-first approach, there are two well-known prior works. Between 2019 and 2021, my friend Jonathan Leichu, who is a prominent security researcher, used automatic bulk pull request generation as a scalable methodology and launched several bug reporting campaigns. What he did was he identified a bug, then went to GitHub and searched for all the applications or code signatures that may harbor such a bug, and then used an automatic mechanism to rewrite those applications so that a fix is produced, and then create bulk amount of pull requests to mitigate those bugs. In 2022, researchers from Trellix followed up on Jonathan Leichu's work and then proposed over 60,000 patches to fix a CVE that has been a 15-year-old vulnerability, but was still available in a lot of open source projects. The depth-first approach has several problems. First of all, this is only limited to shallow bugs. Because you're doing a wholly automated process of rewriting into many different kinds of applications, each of which has their own nuances, the fixes that you generate may be only limited to shallow bugs, or if you overreach, you make a lot of mistakes and therefore you annoy maintainers. A term called drive-by pull requests or drive-by PR has been adopted by the maintainers and in the open source software industry in particular to describe this phenomena. Drive-by PR basically means that a security researcher has found a bug but has not done in-depth analysis to see whether this bug actually matters. For example, you find a possible attack, but it may not happen in an application because of the attack surface that is available in that application. In that case, a security researcher reports a bug, but the maintainer says, hey, this is not relevant to me because I don't do things this way or that way. But in drive-by PR, the security researcher does not bother. He has already driven by. So the maintainer has nothing else to do but close that PR and then have a beef on his mind. The next time a drive-by PR happens, I better not listen to that, because that was just busy work inflicted upon me without any actual benefit. So you'll see comments like this, like unimportant drive-by robot submission, or not a critical fix, as this is only local unit test code, which basically means that the security researcher failed to understand the nuances of the application. Before we embarked upon this project, we did a fire hose style interview. What we did was we went to those maintainers who were not happy about these drive-by PR submissions, and we asked them what made them unhappy and how could we mitigate and improve upon this interaction process. We identified 4 key issues. One was that the bugs that are reported are unimportant and shallow, and they're not worth the maintainer's time. The second problem that the maintainers had, that the suggested fixes by the security researcher, because it was automatically generated, it often breaks code and have other bugs. So the maintainer has to do more work in order to validate the fix in the first place. Also, oftentimes, because the drive-by security researcher reported and moved away, and the reporter is therefore not participating or following the norms that each of the projects have. And finally, the reporter may be a bot, as is true in the case of Trellix and the work by Jonathan Lechu presented earlier. So before we started the project, we wanted to create a policy that would address the 4 key issues identified before. We decided that we would triage the bug reports presented by intelligent code repair and other static analysis tools manually and only concentrate on high and medium severity bugs. We adopt a semi-automated approach and created a triage portal that will automate the reporting process. But a security engineer will always initiate the process and will follow the norms that are set as defined in the project's requirements, like the security.md file. The team members work with the maintainers and follow their norms. In order to motivate maintainers that a fix is needed, sometimes the security researchers also created proof of concept exploit code to demonstrate the impact of the bug. And finally, the bugs are reported from handles that belong to human beings so that they at least do not appear to be reported from a bot. These tweaks definitely paid off. But before I go into the results, let me touch one other aspect, which is how are we able to scale to many projects? This is where the precision of ICR helps to scale the effort. ICR finds bugs that other tools miss and do that with dramatically low false positives compared to other tools. Here we provide a couple of examples where ICR and another bug detection tool, when run on a single application, the results of ICR are much richer than the results of others. Compare this with Sonar Cloud on Epicurio Registry, which is a Java application written by Red Hat. Sonar Cloud identified over 1,200 bugs, and the majority of them, 92%, were false positive or won't fix issues. ICR, on the other hand, only identified 111 bugs, of which there were only 6 false positives. Moreover, ICR was able to synthesize fixes for about 95 of those bugs identified, or about 84% of the cases. This is extremely useful because our security researchers are only looking at a high concentration of true positive bugs, but at the same time, when they're looking at the bugs, they also have the fixes readily available. So when they're reporting the bugs, their job becomes much easier. The same happens for Django. When we ran ICR as opposed to Bandit, which is an open source bug detection tool for Python developers, Bandit had 94% false positive rate compared to ICR with only about 11% false positives. In this case too, for about 52% of the cases, ICR was also able to synthesize a fix. Also, when we are reporting the bugs, we are focusing on the bugs that matter. So we identified the CWEs, or common weakness enumerations, that resemble the top 10 OWASP security vulnerabilities and only concentrate on those. For example, here is a cross-site scripting averted in Red Hat's code, or this is a data race that has been averted in Kubernetes code. We also needed to follow the responsible vulnerability disclosure mechanism. When we are thinking of critical security bugs and we reported that publicly, that might create a zero-day exploit, which we clearly do not want to do. So here is a draft proposal which outlines an activity diagram of what you need to do to report a vulnerability in a responsible manner. This is not meant to be read. but it shows the many paths that you need to follow in order to report the vulnerability properly. There are many different outlets to report the vulnerability in a responsible manner. The most recent advances has been made by an approach called the private vulnerability reporting, which is done by GitHub and GitLab. You can also create a pull request for bugs that are not that critical. You can also create an issue when you do not have a fix readily available. You can create a GitHub security advisory to report certain kinds of bugs. Finally, in some cases, the security.md file maintained by the maintainers asks you to report the vulnerability directly by email or report in a separate portal like BugCrowd or HackerOne. In each of these cases, we followed the norms and did exactly what the maintainers wanted us to do. So we created a triage portal which was semi-automated, as in the bugs that we wanted to report, many of the fields that are there are pre-populated by us. And the triage portal also implements a subset of the vulnerability reporting proposal that I was referring to earlier. This helped us work in a more efficient manner. Most importantly, I mentioned earlier that communication is the key. We have to work with the maintainers to convince them to fix a bug in certain cases. This is especially true for security hardening cases or simple logical bug fix cases. The maintainers might say that I don't care about this. But as we worked with them and explained that the bug, although appearing to be benign, could create some bad scenarios, then the maintainers eventually agreed to fix those bugs. In these cases, the proof of concepts or the explicit demonstration often helps. Like on the screen on the left side, you see that we reported a bug to update a module name to allow import without type errors. And we created a very simple demo that shows that a crash happens when that project is to be imported. As such, it is easier for the developers. When they see the crash, they understand that even though this is a very simple fix or appears to be a very benign error, it might actually create problems downstream. So they went ahead and fixed the bug. The work that we are doing is all publicly reported, and the information is available for everyone to consume. Right now, we are looking at 6 key performance indicators as we are aggregating the results month over month. We're looking at the number of projects that we are scanning every month, the number of bugs reported in that month, and among them, the number of security or reliability bugs that are reported, the number of patches that are generated, the number of fixes that we also generate and report, and finally, the number of bugs that have been fixed, as well as the number of security and the reliability bugs that have been fixed. In the recent past, we have scanned over 3,500 applications. We have reported over 300 plus bugs. Of those, about 120 were related with security and reliability, about 40 of them high severity, and the bugs that we have reported, 51% of them have already been fixed. The results are available in the link that is shown here. Before I leave you with the key takeaways, I want to give a shout out to the security researchers who are behind the scan and did majority of the work explained here. A couple of these researchers, Ataf and Zuhair, are at the audience. And since I'm not here physically, they will be acting as my proxy to answer any questions that you may have. So what are the key takeaways? Open source project maintainers need a lot of help from security practitioners, and the security practitioners should communicate with the maintainers in a meaningful way so that we don't have conflicts or tensions between these two parties. OpenRefactory's work has demonstrated a model of engagement that shows promise, and in the process we have cleaned up a significant portion of the beach and have made those signals available for end users to use. Thanks a lot for listening to my talk. We'd be happy to take questions.